He is the chief scientist at this Quantinuum. This is a quantum computing company. Before this, he had been on a distinguished chair at Perimeter Institute. And Bob does actually very different and very interesting kind of work. He is famous for introducing a sub area of quantum mechanics, which goes by the name of categorical quantum mechanics, which involves interface with, pictorial view of things, music, and he even connects to things like computational linguistics. So, and for students, you might find online it's very interesting lecture notes called Kindergarten Quantum Mechanics. I urge people to have a look at it. So, completely pictorial view of whole of quantum mechanics. So, I'm sure today we will get a glimpse of this very interesting view from Bob. The title of his talk is From Quantum in Pictures to Practical Natural Language Processing Music and Understandable AI.
Okay,
Bob,
thank
over
you.
to you.
So I'll start with, I'm going to close my door. People are too loud here. Oh, okay, here we are. So I'm going to share my slides.
Yeah, sure.
Share screen. So where are that? Those are the slides I want to share. Share and view enter full screen. Okay, here we are. So yes, my name is Bob. I'm the chief scientist at quantum computing company Quantinuum, who are actually going to make a very big announcement today, later in the afternoon in this time. I'm an emeritus fellow at Wilson College. They effectively organized a retirement party for me, so that was very interesting. And I'm distinguished visiting research chair at Perimeter Institute. So that's my second affiliation. Okay, so just to say a bit more about my history. For a long time, I was a professor at Oxford University in computer science. I'm a physicist, but in the sort of stuff I was doing, I would never have a chance at the time to get any appointment in physics department. So the Perimeter Institute is a very nice thing to get this now. So we had a very big group. This was Samson Abramsky and myself. This was a big interdisciplinary group with many people many of which actually moved with me to Quantinuum. In 2020, I left Oxford University. Well, I'm still there. I'm still teaching and still supervising, but in terms of like a faculty place. And then I joined something which was called Cambridge Quantum. First Cambridge Quantum Computing and then Cambridge Quantum. And I became chief scientist there. But then again, in 2021, Cambridge Quantum was no more. And the reason, it's not that it vanished. Basically what happened is it merged with part of the big American company Honeywell. So part of Honeywell split off from Honeywell, the part which were building quantum computers, and they merged with us. And this afternoon, there will be a big announcement again concerning building quantum computers and bringing them to a next level. So that's where I'm now. Besides my global role in the company, I also have my own team in Oxford, and we focus very much on sort of the interface between artificial intelligence and quantum. And so a lot of these people here actually moved with me. Some of those names will come up in my talk. Okay, so that's our logo. So what this stands for a C and an I, compositional intelligence, because I see no reason why intelligence has to be artificial in the first place. Like, we are intelligent and we are not artificial to start with. And then compositional is basically the sort of structures we try to bring in. There's now a lot of debate and chat, especially after Hinton announcement, that the brute force machine learning stuff may be quite dangerous for broad use. So the meanings in that direction are clearly growing. And so you need something that's more interpretable. And what we are doing is an example of more interpretable in AI. It's kind of nice that it also looks like a Q. So it's quantum compositional intelligence if you want to. This logo was designed by one of our team, Konstantinos Mechanisidis. And I'm going to now take a time machine back in time to close to the beginning of the previous century, and where the language that we use to talk about quantum came about. So this is John von Neumann. John von Neumann is the father of the Hilbert space quantum formalism, which pretty much everybody still uses today. And he published that formalism in a book in 1932. In 1932, he published this. But in 1935, something very interesting happened, which you don't see much. So John von Neumann basically denounced his own Hilbert space formalism only 3 years after publishing his book. So I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. And then a big portion of von Neumann's career, as far as physics is concerned, was to try to look for alternatives for Hilbert space. One thing was called quantum logic. He also came up with phenomenal algebras and things like that. It's fair to say that none of them actually are now at anywhere close to a status that it's a substitute for Hilbert space. Honestly, they all vanished. They basically all vanished, and they're only in very marginal ways still being used. So on the other end, I should say that each attempt of von Neumann to come up with a new quantum formalism resulted in an entirely new field of mathematics. So he wasn't a complete failure at all in that extent. Now one thing I should say here is the idea von Neumann had, because he's also one of the fathers of quantum foundations, is you need to focus on what's the most important feature of quantum mechanics, what is the characterizing feature, and then we should conceptualize this and maybe abstract it and formalize, and that's the path towards a new quantum formalism. And for von Neumann, the most important thing about quantum mechanics was quantum measurement. What happens in the measurement process? For example, quantum logic was like, if you want to reason logically about quantum system, but the fact that you have collapse sort of changes your logic completely and logical structure. So these were the things von Neumann was focusing on. And most other people who were considering the foundations of quantum mechanics always had this particular focus on measurement, which was always at the core of quantum foundations. Now, this is Schrödinger. So Schrödinger was around at the same time. And Schrödinger had a very different opinion than von Neumann. So he's talking about here, this is his paper, also 1935, same paper, same time as when von Neumann denounced Hilbert space. And he's talking about two systems, when two systems, blah, 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 and then he starts to talk about how quantum systems behave when they come together. And then he says, I would not call that one, but rather the characteristic of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So Schrödinger's view was the most important thing about quantum mechanics is the tensor product, not the measurement process, is what happens if you bring two systems together. And like I said, pretty much everybody in the foundations and quantum formalism was following von Neumann until fairly recently. And that's with a paper with Samson, Abramsky, and me wrote, which was the start of categorical quantum mechanics, which was mentioned earlier. And so basically, we kind of start to realize Schrödinger's view by coming up with a formalism which takes composition of systems as a first-class citizen. So it was actually, in order to make that meaningful, we also move away from a perspective of states, describing things by states, which are sort of static entities, to processes. So we have a theory of processes, and these processes can be composed sequentially, but also in parallel. That's actually the base, that's a monoidal category. There's nothing more to it. You've got processes which can be composed sequentially and in parallel. So we used this framework of monoidal category theory, and then we added some structure to it, a tiny bit of structure, a little bit of structure, and then we were able to basically define unitarity. We could derive things like quantum teleportation. And so we had already a quite expressive formalism with very little ingredients. There was like Born rules, there was number. So it started to look like a quantum formalism. This is now a paper which is quite famous. But the problem with this is not everybody is like a hands-on in category theory. You don't even have to be hands-on in category now, but at the time this was very much formulated as a category theory paper, and it's not everybody's bread and butter. But okay, so let's go to somebody else. So this is Roger Penrose, also at Oxford, also Nobel Prize winner, of course, for black holes and stuff. But something else Roger Penrose did was at some point, and he started this already during his undergraduate years, when he was learning general relativity. He really didn't like this sort of indices which people use in tensors, like the Einstein notation type stuff. He hated it. And he kind of realized that you could equivalently represent these things by graphical entities. So you see here this QIABCFG, he replaces by a blob or a box or whatever you call it, with some wires coming in and some wires coming out corresponding to the indexes, which it has. And he came up with notations you see for many other tensors. So this goes back to the 60s, I think, to the 60s even, definitely early 70s. And it only appeared in one paper, really. It only appeared in one paper, in an appendix even, I think, of Penrose. So it was never a prominent thing in the literature. It was just a tool which used like behind the scenes. Now, these two people are two category theoreticians, André Joal and Ross Street, and they actually realized that monoidal categories I was talking about earlier and these sort of diagrams Penrose was drawing are exactly the same thing. Or they're equivalent for all practical purposes. I can't go in what the precise notion of equivalence is because it's quite complicated, but you never have to, you can just think that they're the same for all practical purposes. That's kind of what it means. And so I wrote a paper which was earlier mentioned, Kindergarten Quantum Mechanics in 2005, which was pretty much the same content as the previous paper with Sampson, but which was not formulated in terms of category theory, but rather in these sort of Penrose-like pictures. It was the same content, but now Penrose-like pictures, so much more easily accessible to a broader audience. And at that point, I mean, the plan for me was, can we, on the one hand, complete this theory of categorical quantum mechanics, so turn this into a full-blown quantum formalism in which you can do everything, which you can do in Hilbert space, or equivalently, can you come up with a purely diagrammatic presentation of quantum theory? So can we also have all these ingredients that we would need to axiomatize in category theory? Can you also always turn this in diagrammatic way? And then the third way to say it is, can we formulate quantum mechanics as a theory of processes, where the processes and their composition are the main actors? And so this is the sort of language one uses in there. So this is the main axiom you find in kindergarten quantum mechanics, and all it says is, if you got a bent wire, then you can yank it. It looks like a really silly axiom, but it's actually this is the sort of thing that lets you derive teleportation. This actually, in a logical sense, is sort of like a deduction theorem, although it looks very silly. And then if you got a box like that here, so you got this box, and so we typically in this talk, in this part of the talk, we will read these diagrams from bottom to top. So what you got here is basically a box, which you think of like an input-output device. And the wire bends the output into an input and the input into an output. As it turns out, this corresponds exactly to taking transpose in linear algebra. So this is the way you can define the transpose during this cup and these cap-shaped wires, which you also see in this equation. And then you can then do just the following. You can just yank the wire, and then that box rotates 180 degrees. So actually, you have now derived that just rotating a box with 180 degrees is pretty much the same as taking a transpose. And so you can have an entire presentation of linear algebra with transposes, conjugates, unitarity, inner product, and all the sort of stuff from linear algebra just represented within this language. So that's something you find in this kindergarten quantum mechanics already. Now, okay, so these were the early years, 2005. We weren't able at all to derive or describe anything you can do in Hilbert space quantum mechanics. We are nowhere near at that time. But then 13 years later, there is this book, which I wrote with Alex Kissinger. And this effectively is a full course quantum computing, which is still being taught at Oxford by Alex Kissinger, and which I had been teaching for a long time. But this is a full-blown course quantum computing, and everything's presented in terms of this picture that I was talking about. So so the theory, of course, advanced quite a bit to actually achieve that. And what we do, it's quite a big book because, of course, we're not going to teach people only diagrams because then they can't read anything else. So in this book, we start introducing everything by means of the diagrams, but then we derive linear algebra from the diagrams. We derive linear algebra, we derive the usual Hilbert space formalism all from the diagrams. And then again, these pictures are quite big, so you easily get a big book, but we typically teach this in 20 hours. So the number of lectures to teach this is typically 20 hours. So it's much less than it may appear at first. Okay, now it is a university level book still. I think when we wrote this, what we had in mind is like university students, mainly who have some linear algebra background already, although we derive it, but it's probably much better if you have it already to actually get through all that stuff and so on. So it's definitely not kindergarten quantum mechanics. It's definitely not for kindergarten. Okay, now we are 5 years later, and now there is this book. It's new. It's called Quantum in Pictures. It's out since 1 or 2 months. Unfortunately, at the moment in India, it's only available as Kindle. We're working on it to change that. There's a reason we did it. We actually published this as our company, just to have full control. And I can say the philosophy behind this publication. But since we are not an established company, it's not so easy to actually do all of that. So we use something which is Amazon print on demand, which gets printed in the country you buy it. So you don't need distribution, you don't need storage, nothing of that. But it's not available in all countries, unfortunately. But now we're working on it. We're trying to get a distributor who can actually bring it to everywhere. But so for now, it's available as a Kindle in India. And this is really a book that is readable by people who don't have any maths background and want to learn about quantum. So we already have reviews from, like I'll show later, from a 10-year-old, for example. So this is really a quantum formalism accessible for people without mathematics, but it's but it essentially covers the same content as we cover in the big book. So it's pretty much a full-blown quantum computing course without the Hilbert space formalism. So there's things in there which you don't even find in regular courses, like measurement-based quantum computing, no broadcasting theorem. So there's some pretty advanced stuff in there, but presented in a way that everybody who wants to can pretty much learn this. Now, what is soon going to be forthcoming and available everywhere in the world without any restriction is a lecture series of that book. And we're going to just put this on YouTube as a lecture series so everybody can watch the lectures of this entire book. And that'll be soon put online on YouTube. Okay, I'm going to briefly take to like a tiny bit of the content in this book, just to give you an idea on how this formalism has evolved. So we already talked about wires and boxes. So basically the idea is you think of a wire as a system and of a box as a process that acts on that system. So this could be like a wire could be a quantum particle, the box could be like a quantum gate or something like that, or it could be a measurement from quantum to classical, or it could be just an electricity device or a water pump, if your wires are places where water flows. So it's just a generalized thing. And then what you can do is you can compose them. And you see, we both compose them sequentially. Some boxes come before other boxes, and also in parallel, some boxes are besides other boxes. And that's sort of the basic formalism. And you have these two composition operations sequentially, and then the composition of systems, well, here and processes. If you see two wires side by side, it just means these are two systems. So we actually start effectively, but we've given composition of systems the sort of lead role in this game. It is the lead player. We saw this equation already, and so let me now go in more detail. Now that I told you that these wires correspond to systems, then you see the cup-shaped wire at the bottom is basically something which has no inputs. If you treat this as a box, and two outputs. So it's a state of two systems, and actually this is supposed to be the Bell state. So this cup-shaped wire is actually the Bell state. Whenever you got a box without inputs, it will always represent a state. On top, you got like a cap-shaped wire, which you want to treat as a box too. And this is like an effect or a test. This is actually the Bell effect. And the Bell effect corresponding to the Bell state just by going from a cat to a bra. So that's really what the thing on top is. And so if you think about this now, this is actually a non-trivial equation. You got an open wire left bottom, so this means there's a system particle coming in. Then you got this cup-shaped wire. This means a bell state is created. So suddenly we got 3 particles going on, and then on the top you've got this bell effect, which means 2 of the particles vanish in a post-selected measurement, and then this equation says doing all of this, do all of this at the same time is basically the same as doing nothing. A plain wire is just the identity. Plain wire is just the identity. So this is a non-trivial equation, and I mean, you can do fun things when you got this cup-shaped state. You see, we've got the box there on the left. We just slide it to the other side. It rotates 90 degrees, which means having an operation on the left is the same as doing the transpose on the right. So that's what this shows. This calculation shows. If I've got a bell state and I do an operation, Alice does an operation on the left, it is exactly the same effect as Bob does a transpose on the right. It's the same thing. So that's what this equation is saying. And here we got like post-selected teleportation. So all the shape of this cup and this cap together is really basically quantum teleportation. So here you see Alice and Bob who share a bell state, like the cup-shaped thing. And then Alice does the post-selected effect, bell effect. And then you can just slide that box without an input, so nothing comes out. Slide this box all the way to the other side. And so whatever, and that's state because it doesn't have input. So whatever state Alice has there ends up at Bob's side. I mean, I'm going very quickly over this in the book. This is many tens of pages to explain this all in detail. And then, of course, this is not full-blown teleportation. It's just post-selected. So basically, you see this unhappy phase on the left. That's actually the error that actually allows you to take one of the 4 different effects in a bell measurement, like via Choy-Jamalkowski, but then you can slide this box to the other side, and then so you see, when you would slide that box to the other side, it's actually the edge on of the box on the left, which means if you take these boxes to be unitary, which they are, then they vanish. So this is full blown, and you got this wire in the middle. Now this wire in the middle is an annoying thing because is not part of the picture, but in the full blown formalism, we can represent classical and quantum also in the same formalism. I'll give an example of that later. Okay, so now this is all about these cups and these caps and these wires, and that happens to be not good enough to capture all of quantum. You need something more. Okay, and the thing you need more is something we call spiders. So, okay, so what is a spider? In order to understand what a spider is, we need to understand what a wire is, because spider turns out to be a generalization of wire. So what is a wire? A wire is a thing that connects 2 endpoints. You see here a wire and it has 2 endpoints. And now, so this is what a wire is. And now what can you do with a wire? What can you do with a wire? Well, if you glue 2 wires together, you take an endpoint of each of them, then you get again a wire. This is sort of the theory of being a wire. If you connect 2 wires together, you again get a wire. And there's nothing new which comes about. So it's quite a limited concept of wire. Now, what is a spider? You have to think of a spider as something like a wire, but not with 2 ends, but with multiple ends. Any number, or none, or 1, or whatever. So the number of ends can vary. That's the difference. And the behavior of such spiders is exactly the same as behaviors of wires, or generalizes it in the sense if you block 2 spiders together, then they fuse together, just like 2 wires fuse together. Of course, now the number of legs of the resulting spider may be different than the ones you start from, because you just have to count the numbers and keep them up. Here on the left, we got like, here is one with 5, there is one with 4, and we end up one with 7 wires. So that's spiders. Okay, so this is theory. Let me now just go a little bit off slides. So what's happening behind the scene here, say in Hilbert space, in the case that suppose you interpret these spiders in Hilbert space, the way you would do that is, let's say these wires, they correspond to qubits. They're represented by 2-dimensional Hilbert space. And if you put two wires side by side, it's a tensor product of these qubits. So at the right-hand side here at the bottom, we got a tensor product of 3 qubits, and at the top, we got a tensor product of 4 qubits. Now, so okay, these are my types. Now assume that these green things are linear maps. So the one on the right, spider on the right, is a linear map from tensor product of 3 qubits to tensor product of 4 qubits. These equations, which I write down here, this fusion of the spider together with its symmetries, is enough to prove a theorem. And the theorem is, in Hilbert space, each such family of spiders is in one-to-one correspondence with an orthonormal base. So this is a way to define orthonormal bases in a language where you only use this tensor product. So you can define orthonormal bases just using tensor product and for linear maps. You don't need anything else. You don't need an idea of sums. You don't need a notion of sum. You don't need to know coordinates and linear combinations and all of it. You don't need all of that. You can just do it with the tensor product. So this is a result very much in support of Schrödinger's thinking, I would say, because once you got orthonormal bases, you're getting close to measurements. And you can actually do this. You can actually use these spiders to define measurement. So measurement can be derived from the tensor product. And that very much fits into sort of Schrödinger's thinking. Okay, so we now, whenever you see such a family of spiders, and we're going to distinguish them by colors, you have to think, I'm seeing an orthonormal basis here. I know it's weird. It's weird. It doesn't look at all like an orthonormal basis, but it is an orthonormal basis. Each is family of spiders. And okay. So what do we see here? We see two colors of spiders. So this means we have two families of spiders. So we have two orthonormal bases. And we have an equation here. You see there's an equality in the middle. And what is the equation saying? For these two families of spiders, if they share two legs, and this has to be two, not one, they share two legs, then these legs go away. So they disconnect. They disconnect. What does this mean for the corresponding orthonormal bases? It means that they're actually mutually unbiased. This is a definition of mutual unbiasedness of two bases. So again, it's not maybe what you would expect to be, but that's what it is, exactly on the nose. So you can define mutual unbiasedness in this way. And for example, examples of bases which satisfy this equation would be the Z bases and the X bases for qubits, because they're mutually unbiased. In the old language, people call this complementary. So we have got here these complementary spiders or mutually unbiased bases. What do you want? And they satisfy this. So let's recall our equations. Spiders of the same color fused together. Spiders of different colors. When they have two wires between them, these wires go away. And now let's see this on a very simple calculation. This is a totally trivial calculation. So as it turns out, if you take the green spiders to corresponding with the Z bases for a qubit, and the red spiders corresponding to the X bases, and you connect just look at the thing on top, like just look at the horizontal wire between a red and a green on top. Turns out that this is the C0 gate. You build a C0 gate by taking a red spider and a green spider. Now, you probably don't understand what I mean by a vertical wire, horizontal wire. Horizontal wire means it doesn't matter whether I actually take these wires in between them as an output or an input or whatever. It doesn't matter. It's always the same. You always get the same because of the symmetries of the spiders. So that's why we write it as an horizontal wire. So this is what we got here really is three C0 gates. We got three C0 gates here. We got three qubits. And on them, we have three C0 gates, with the green dot being the control and the red were potentially unigate. Right? So now we want to simplify this circuit using our spider rules. Okay, let's look at it. Which rules can we apply? Well, I mean, we see three green spiders, which are connected, two red spiders, which are connected. So in the first step, we just fuse them together. We just fuse them together. Okay. So that's our first step. We fuse them together. And now we see there's two wires between the red and the green. Okay, they fall away. So they go away. It's two wires between different spiders go away. And now we got a wire with a spider with two legs. But yeah, that's just a wire. We know that because spiders generalize wires. So we actually get this. So we were able to simplify this circuit to this circuit using the spiders. This is a very, very simple example, super simple example, super easy example, of course. But this method generalizes, and this method now constitutes the state of the art on how to simplify quantum circuits. So using this spider language and all that provides us with the best way to simplify quantum circuits. So this method is, for example, lives inside the ticket compiler. So Quantinuum, we have it's more than a compiler, but part of it is compilation, and it uses this method to simplify its circuits because it's part of the state of the art to simplify circuits. So that's pretty cool. Okay, so this is a very easy example. Now I'm going to go much closer to the end of the book. Okay, so this is a picture, and you see a lot more going on here. You just ignore like these wires which go between this red dot and this green dot. They're like a little bit like see, there are some cracks in it. Just ignore them. They mean nothing. They mean nothing. So what do we see here? We also see that some of these wires are double. Some of these wires are drawn double, and some, like the one with these cracks, are drawn single. Well, when you see double wires, you have to think quantum. When you see single wires, you have to think classical. So in this picture, we have both quantum and classical things going on, because we see double wires and we see single wires. What else do we see? We see at the bottom a red double dot, We have like 3 double wires coming out. That is actually a GHZ state. That's a GHZ state, the GHZ state. And then you see these red double dots with 1 double wire coming in, 1 double wire coming out. They're actually phase gates. They're phase gates for the X observable. So not the usual phase gates for the Z observable, the ones associated with the X observable. And and when the angle they carry is basically the rotation they do. So in fact, the double red dots with 1 in and 1 out, they're actually just identity. They're zero phase rotation, but just for clarity, we put them here. So what you see here, and then the green dot, which goes from 2 to 1, is actually a measurement. It's a measurement in the Z basis. It's a measurement in the Z basis. Because it's green, it's a measurement in the Z basis. Okay, so what we see here are 4 GHZ states on which each case 3 measurements are done, but because of the rotations, these are different measurements each time in each of these 4 scenarios. So these are actually the 4 scenarios of the GHZ Mermin non-locality proof. These are the 4 scenarios you consider. So you do all these 4 scenarios, and then what you do, if you know maybe you don't know the argument, but the argument is then you take these 4 scenarios and you do a parity check. You look at all your outcome of these measurements and you measure parity, the overall parity. So this red dot with single wires is actually a parity check, or you can, it's an XOR, you know, parity and XOR is the same thing. So it's a big XOR if you want. And okay, so then you can compute this thing, and I'm just going to get, I'm going to informally say what happens if you do the computation. All at the bottom, all the red dots, they fuse together. All the red dots, they fuse together. And then on the left-hand side, we got no angles. On the second one, it's under 80. The third one is under 80, and the fourth one is under 80. Because when spiders with decorations, so these spiders, they carry decorations. So we generalize our spiders to carry decorations. When the spider with decorations, when they fuse, these decorations add up. So this is a new concept which I didn't introduce yet, these angles on the spiders. But it's something which exists for just abstract nonsense reason, really generalized nonsense reason. But every spider naturally comes with these phases, and these phases always form a group. They form a group which we call the phase group. So, okay, so in this calculation, we have now all these red things having fused together. And then it turns out that from the equations of spider interaction, you can actually commute the red dot and the green dot. And then this red dot is on top, and they all fuse together. That's really the calculation. You find this in our book. In both books, you find this calculation. It's not difficult, but I haven't given enough background to do it properly. This is actually on page 120 or 130 we're talking now. And then basically you got all these angles are going to add up, and we got 180 plus 180 plus 180 gives 180. And it turns out the red dot decorated with 180 is the 1 bit, is the bit, the classical bit 1, is 1. Okay, now here we see a different diagram, and what this actually is the articulation, the expression of locality. So that the existence, the fact that there is no local hidden variable theory possible. So what you see here, these boxes at the bottom are actually, so you see on each particle here, there are 2 possible measurements, either with 0 angle or with 90 degrees angle. So these 2 boxes, the one without star correspond to the hidden variable for the measurement with 0 angles, and the one with stars for the hidden variable for the measurement with 90-degree angles. And we do this for each of the 3 systems of the GHZ state. So that's what these variables on the bottom do. And then we copy these variables out, these classical values out, to the different measurement scenarios which live in the middle. I mean, you probably can't map, but at some point in the middle, you'll see there are 12 wires, which correspond to the 12 wires coming out here. But now as an hidden variable, as a local hidden variable. And then we do the parity thing again. So this is the expression that this is the statement or the assertion that there exists a local hidden variable model for whatever happens in the previous scenarios. Now, you see, if you look at the green dot and the red, there are always exactly 2 wires between them. There are exactly 2 wires between them, so they fall away. So what we end up at the top is just a red dot without an angle, and that turns out to be the classical bit 0. So quantum gives 1. Hidden variable gives 0, contradiction, there is no local hidden variable model of quantum, and that's exactly what the Nobel Prize this year was given for. So this is the diagrammatic proof. This is the most complicated thing you find in the whole book, but it's actually not complicated if you've gone through the whole theory. But it should show, so for example, here this is Dan Gicca who posts a review, that was on Facebook, I think, from Alexander Gicca, his son, age 10, on the new book, and he understood everything. So it's 10-year-old, he understood everything. So even states very well structured, easier to understand than science YouTube videos. So, okay, so that's good. Now, of course, this is just one person. So what we are doing now at the moment, and this is in collaboration with Oxford University and IBM, is we're setting up an experiment in which we teach teenagers quantum through our new book, so they don't need any math background. And at the same time, we're going to consider a bunch of Oxford students who take a regular quantum computing course, and we're going to subject them to the same exams. And then we're going to see who performs the best. So the timeline now is that we start our lectures, because we've got these video lectures, that will be the lecture for students, then they will get some tutorials and things like that. They would get the regular course. So we already have been collecting volunteers, so that's all done now. And so the next thing is basically to educate them in quantum. We use exactly the same time frame as courses at Oxford University take, and then we're going to give them an exam in the same format as Oxford University, of course, formulated in terms of pictures, because otherwise they wouldn't understand the question. They don't know Hilbert space. And then the Oxford student get the same questions formulated in Hilbert space. So that's going on now. And then we hope to show that effectively teenagers can even outperform Oxford University students on certain tasks with these diagrams. Now, what's the origin of all that stuff I've been talking about? The origin of all that stuff I've been talking about is something called ZX calculus. So the name because he was sort of an axiomatization of Z and X observables on CRX basis, but it's actually much more general than that. But the name ZX calculus has stuck, and he was Ross Duncan, who's now the head of software at Quantinuum, and myself, who came up with that in 2007, so quite a while back. And for some reason, it didn't pick up very well initially. It was very weird. It was interesting sociological observation. People for a long time the mainstream community for a long time didn't believe that something that looked so simple could actually be useful for anything. And they never even bothered to study, they never bothered to learn, they just had a judgment as a mainstream community. Okay, that stuff. People kept work, some people kept working on it. We started further, we kept further developing the theory and stuff like that. And then a few years ago, there was a complete switch. And because quantum industry came about. So quantum computing is becoming closer to something practical and has practical needs like making circuits as simple as possible, error correction and stuff like that. And suddenly people start to realize, initially in quantum industry, that this stuff is super useful actually. That this stuff is not just useful, but necessary for many practical applications. So the domain where I think it's now most widespread use is photonic quantum computing. So companies like Quantum, who are trying to build a photonic quantum computer, are using this basically as their main language. So they're now using ZX calculus as their main language to describe things, not Hilbert space anymore. The reason, of course, they do measurement-based quantum computing. Measurement-based quantum computing is horrible in Hilbert space, just horrible. While actually, historically, ZX calculus came out of problems in measurement-based calculus. So measurement-based quantum computation. So they go very naturally hand in hand. And so here you see that ZX calculus is immensely useful graphical language for blah, blah, blah. So they use it as their main language. PsiQuantum is the biggest photonic quantum computing company in the world. And then the cherry on the cake recently, this is very recently, we're talking 2023, is if a paper came out on error correction with Peter Shores co-author, and he's advocating the use of ZX calculus for error correction. It's even stated there that everybody doing error correction should be using ZX calculus probably. So suddenly there was a complete change, and then it's now fully embraced by quantum computing world and all that. And okay, this is so there are two dimensions here to the story. One dimension to the story is the educational value of this formalism, because it actually can make quantum much more inclusive than one would have expected with the Hilbert space formalism, because many more people can now learn quantum through these pictures. And I think this is very important, especially with what has been happening recently in AI. In AI, a bunch of people just went wild, like they were like wild cowboys, and they did whatever, and nobody understood what they were doing. And now we're in this situation that actually we're stuck with something that seems quite dangerous. With one of the fathers of the field, Hinton, denouncing his own work basically, and that he's sad that he actually did it, and that this maybe shouldn't have happened, and it's a very dangerous thing. And by making quantum more inclusive, we actually can avoid such situations which have been happening for AI. So that's the educational side, and then the other side is what I'm just saying here, that is really very important for practical quantum computing, these diagrams. People now want to use this because it solves problems which are otherwise hard to solve. Like I already said, circuit simplification, so it's widely used for error correction too, in many different ways. There's many other, like I said, photonic compilation, many different applications now are using these diagrams. I mean, this is now an outdated slide, but this is the places I was aware of at some point where they're using these diagrams for some reason or another. It's not just quantum computing companies, it's lots of different kinds of companies that you see here. They're using them at NIST. For NIST were actually one of the early ones where they were using them. So yes, you see NASA, so they are now really widespread used. And I'm probably missing so many out here because I stopped catching up. And there's probably some who just don't say it. Right, so why is this language so powerful? Why is this stuff so powerful? Well, this is a theorem from, essentially the main theorem came out in 2018, where people in a number of stages have shown that any equation you can derive using Hilbert space, linear maps and all that, you can derive with these diagrams too. So there's nothing more equations that you can derive in Hilbert space than whatever you can do with these diagrams. So they are, that's the technical term which logicians use, they're a complete axiomatization of Hilbert space. They're complete. That's where this works. So of course, they're of course also universal. Also, otherwise they were were pretty useful. So what I mean by universal is you can write down any matrix in terms of the spiders. Any matrix can be written down in terms of the spiders. But what I'm saying now is much more. It's any equation between matrices and whatever you do with them, that can also be derived using these rules of spiders, like fusion, legs falling away, and that stuff. No? You can derive everything you can do in Hilbert space, any equation. So it's a very powerful thing. That's okay. So that's the end of this part of the story. I've got another part which is much shorter, I guess. I want to be clear on this one. And this other part starts with this person. This is Jim Lambeq. So Jim Lambeq is a category theoretician, but he's also father of something which is called computational linguistics. He came up with a system around the 1950s, that allowed you to check whether a sentence is grammatically correct. I'll explain a little bit how this works. So he came up with this system which explains how a sentence is grammatically correct. I'll get to that back. Now, so Jim, unfortunately, he died a few years ago, and but he was a professor at McGill, Montreal, Canada. And so 2005, which is the time I wrote kindergarten quantum mechanics, so the first time I wrote this paper with these diagrams, I was in Montreal and I was giving a talk about, say quantum teleportation in diagrams. Like I said, I showed these people this picture of quantum teleportation and I explained it. And then Jim was in the audience and Jim said, Bob, this is grammar. No, this is quantum teleportation. This is quantum physics. I said, no, Bob, this is grammar. This is exactly the structure of grammar. And he was right. As it turns out, if you look through category theory glasses, the structure of these teleportation diagrams and the structure he came up with different ones. And this was one he came up with in 1999, is exactly the same structure. And I'll show how the sort of things we saw before, the cups and the caps and all that, allow you to actually verify grammatical correctness. So I'll show this. So I didn't care. So, I mean, this was 2005. I was just starting to come up with this new quantum formalism. I just thought of this as a freak artifact, and I didn't take more notice than that. I didn't take much more notice. However, a couple of years later in Oxford, I had some colleagues there, and one colleague was Marnoush Adrzadeh, and she knew about this lambeq algebra, this lambeq grammar calculus. She knew that stuff because she had done it for lambeq. She had developed the theory specifically for Persian. So she knew that stuff. I never even bothered to look into it. Okay, I can say that. And then there was also, I'm going to explain a little bit how this works. I'll be very brief here. So basically the idea of how these grammatical algebras work is you got something called basic types, basic grammatical types. And these are things which make sense on their own, like a noun. A noun makes sense on its own. It can be an answer to a question or something like that. And the noun type, we give the symbol n, and it's a symbol for the noun type. And a sentence, of course, also makes sense in its own right. So the sentence also is a basic type called S, basic type. And then there are things which don't make sense on their own that easily. And an example there is, for example, a transitive verb. A transitive verb because it wants a subject and an object. In English, the subject on the left, the object on the right. In other languages, they may be different, but it always wants a subject and an object. So I'll now develop types for English. And the way you express this, wanting a subject or a noun on the left and a noun on the right, is by you see that symbol. Like I've got an S and then I've got an N on the left with a -1 and an N on the right on -1. These -1 are sort of at the different sides of the ends. And basically what this means is I want, so it's like an antiparticle. Think of it as an antiparticle. So an antiparticle wants a particle to get annihilated. And so here, this is saying this transitive verb needs a noun on the left and a noun on the right so that they can cancel out. Exactly like I show in this calculation here. You see, the three things in the middle are a transitive verb. I stick a noun on the left, noun on the right, they cancel out, and I get a sentence type. And this is actually this is proof of the grammatical correctness of in English of transitive of noun, transitive verb, noun. Now, the important thing is you can actually represent this calculation using a diagram. And the sort of annihilation of this n and this anti-n, so to say, we can represent this by a cup-shaped wire. Same here, same on the right-hand side, we can cancel them out via cup-shaped wire, and the sentence type is retained, it continues. So here you see a little diagram, and this diagram actually witnesses the grammatical correctness, the proof of the grammatical correctness of the sentence now, transitive verb noun. And you can do this for any grammatically correct sentence. For every grammatically correct sentence, you get such a diagram, which witnesses the proof of correctness. So what we have now is grammaticality is witnessed by such a diagram structure, right? And this is nice. Now, we had somebody else in Oxford, and that's Steve Clark. Steve Clark is now our head of AI at Quantinuum. And he knew something else. He knew what I call meaning mathematics. So meaning mathematics is what all the chat GPTs and all now use today. At the time, this was purely an academic discipline, and it's basically representing meanings of words by vectors. So that's what Steve was doing. He was studying the ways you can represent meanings of words or vectors. Yeah, so this was basically about words. They actually had a term, the bag of words. They didn't care about grammar. They just looked at individual words and how meanings can be related. That's what they were doing. So on the one hand, we've got a theory of grammar, and where you compose nouns and sentences, grammatical types. On the other hand, you have a theory of meaning about single words. Now, a natural question is, how can you combine them? Can you combine them in some way? Because we as humans, we basically use grammar to provide meanings of things like sentences. So if you understand the meanings of words and we form a sentence with them and it's grammatically correct, then that sentence is meaningful and we will understand that sentence. We don't have to look it up in the dictionary or something like that. And so can we come up with a mathematical theory where if you know the meanings of the words, and you have the grammatical structure, you can actually spit out the meaning of a sentence. And I mean, so Steve asked this question, he formulated this problem, like we don't know how to combine meanings of words with these grammars. And then I remembered, of course, what Jim had said, that the structure of the structure on the one hand of quantum mechanics, the teleportation stuff, which really is vector spaces and their compositions. So we're talking about vectors and compositions and things like that. Looks exactly the same as the structure of grammar. So it was easy to imagine an algorithm which combined the two using basically our diagrammatic quantum formalism. So the idea is, like, you use the diagrams, they represent the grammar, and what flows in the wires are your vectors, your meaning vectors. So that was the idea we had, and I'll give an example soon. So this came out in this paper, Mathematical Foundations for a Compositional Distributional Model of Meaning, where we start to formulate and this way of like composing meaning, and this is how it works. So what you see here is actually an algorithm. This is an algorithm that computes the meaning of the sentence. The sentence, Alice hates Bob. This is our algorithm. It computes the meaning of sentence. What are the ingredients? What you see on top are the meanings of the words. What you see on top are the meanings of the words. What you see on the bottom are the grammatical structure. And this is now interpreted as a linear map that is applied to these vectors, to these word meaning vectors. So now we're reading from top to bottom, because in English you write your text from top to bottom. But so you see this cup-shaped wire. This is actually now like a bell effect, which it's almost like Bob is teleported into Hades, Alice is teleported into Hades. Hades is like an entangling gate. Think of Hades, it entangles Alice and Bob in a hate relationship, and that's what comes out. That's the meaning of a sentence. The sentence said at the end of the sentence, or at the end of whatever happened, Alice and Bob are entangled in a hatred relationship. It's a very non-symmetric. So of course, a very non-symmetric gate or a non-symmetric relationship. So that's it. And then you can, for example, start to compute inner products. This is like a sideways written inner product, which computes whether Alice hates Bob is closely related to Alice does not like Bob, because using the product to actually compare similarity of meanings. Okay, we use spiders too in this theory. I'm not going to go into that. Okay, so when we came out with this thing in 2010, so people start, I mean, I was telling my co-authors, don't mention the word quantum, because people are going to think that we're crackpots combining quantum and language. And there was all these headlines, quantum linguistics, the quantum linguist, quantum mechanical words, and so on. Okay, but there was some truth about what they were writing. Because what we were doing is we used something that looked very much like quantum mechanical formalism to do linguistics. Now, this is actually not necessarily a good thing. This is not a good thing. Why? Because as Feynman said, like if you're going to take a system like a chemical system or something that is described by quantum mechanics, in our case, this is this meaning theory, then it's going to be pretty hard to do on a classical machine. And we, of course, we did lots of experiments. We got incredibly good results. But with our new theory, but we had a hard time scaling. It didn't scale very well. The reason was these tensors and these meanings, they very quickly became very large and a bit too large for classical machines to do it naively. I mean, we had ways to do it on classical machines, still doing it now today, by the way, but it wasn't the obvious thing. Now, okay, we're much further, and now there are quantum computers around. And in 2016, for example, Rigetti started as a company. And then this is Will Zheng, who did my PhD at the time with me and then moved to Rigetti. And we basically asked the question, now suppose we're going to stick this theory in a quantum computer, this new theory of meaning. Do we get any quantum advantage on top of that? He wants to live in a quantum computer like chemistry, but maybe we get also quantum advantage for some algorithms. And it was very easy to see that for most typical natural language processing tasks, such as classification, sentiment analysis, you effectively get like quantum advantage. You get quantum advantage. Now, this was 2016. Quantum computers weren't that big yet. Okay, now 2020. In 2020, we for the first time effectively did quantum natural language processing. So natural language processing on actual quantum hardware. We did some question answering tasks and things like that. And we got very good result. It worked very nicely. This was still on very small like data sets, small machines and all that. Then, of course, then we start to try to do it bigger, which we did in this paper, QNLP in practice, which is now published in one of the main AI journals since a few weeks. And next thing we did is we took all that software which we had developed to do this quantum natural language processing, and we made it really nice, and we threw it at a public open source. So everybody can now, you can go home and you can do quantum natural language processing yourself. You use our software and it's open source, and you use one of the freely usable IBM quantum computers, and you can just do that, or a simulator if you want. So you can do it yourself. So the software is called lambeq. Not a surprise, lambeq, you remember Jim Lambeq who made this comment, but now with a Q at the end. So this is our paper, and if you want to know how to do the quantum natural language processing with our software, it's all explained in this paper. And it's not, we got like this big international community now with a Discord channel, like hundreds and hundreds and hundreds of people doing this stuff. Now, sometimes for fun, sometimes actually to try to do something useful. Then once the software was out, of course, other teams, other companies actually started to use it. So this is a paper by IBM, who actually tried to even further scale up the size of the type of experiments you can do. So this is an IBM team who did this in 2022, it seems. And this is another IBM team. And they also used our stuff, and they actually did it to start doing quantum natural language generation, which we provide a classifier, and then you can actually also do generation. So that's another IBM team who did has been using our stuff to do generation. They actually wrote a really nice blog post. So an introduction to quantum natural language processing, and it's probably the best place to first read about all the things I've been talking about in a not too complex way, like not at the level of papers, but a little bit more informal, like in a very well-written blog post. So that's a good place to read this one. What did we do? Meanwhile, we did a lot of stuff, but one thing I definitely want to mention is the following. We basically took the linguistic grammar and instead put in a musical grammar. This thing exists. And then we start to generate music on the quantum computer. We generate music on a quantum computer using like musical grammars. And this is a software which is also available, Quanthoven. You can, it's open source, you can get it. And so you can do all this stuff yourself. The funny thing is we generated some songs. One of them was Bob's Cigar Bus. It actually ended up #1 in some classical charts. And I think looking at the time, this is probably a good time to stop my talk. So we've a chart success. Okay, so let me go to the end of the talk. You can follow the things and other talks and publications on Twitter, where where I basically post everything that I think is relevant. Okay, thank you.
Thank you, Bob, for a very stimulating talk. It's now open to questions. So people who have queries, they can ask. Santa, you are muted.
Yeah, I would like to ask a question. First of all, Bob, it's a wonderful talk. So,
Thank you.
when we're looking at natural language processing, do you really see quantum has some natural advantage? Like, for example, when we produce the language, when we come up with grammar, is there any quantum process going on in our brain, for example? Is it reflective of that?
No. That I don't think there's anything quantum about language per se. What is happening here is that there is a certain type of structure, call it a logical structure, which is represented by this diagram and which is pretty much all around us. But we never look through those sort of glasses. And when you look at the world through those sort of glasses, you see that many different things, which you usually don't see any connections between, actually start obeying the same kind of logic, so to say. I definitely wouldn't call this quantum logic or anything like that. It's a certain logic of composition in which, in the traditional world, people always think that most things are separated. Like I got two things, I got a pen and this. But actually, in reality, if you look at the world, things are not separated. If you look at words, they're talking to each other, the words, of course, through the grammar. If you look at people, what makes a human? Human is characterized by its relationship with other people. Not what it's made up, the person is made up from. That's and you see a lot of things in the world are about how things are related to each other. And what this logic is basically expressing is the most simple logic of like non-trivial relatedness. And this makes sense for language, totally. This makes sense for quantum. Quantum is what forced us into looking at these things. With Schrödinger discovering entanglement, suddenly the world didn't exist anymore in physics about separable things. And so it's a logic of non-separability on the one hand. So now, part of your question was about advantage. Of course. So this language model we have now, because of its similarity with quantum, is quite hard to simulate. It's a hard tensor network, hard to simulate on a classical machine. So you already get an advantage on a quantum computer, because on a quantum computer, all this exponential blow-up vanishes. It's very easy to simulate. But now we also think, and this is not in papers or anything, that we could even get exponential algorithmic advantage by doing natural language processing on a quantum computer. To be honest, so what do we do now? Let me talk from the perspective of AI. What we do as compared to usual AI is that we bring interpretable structure into the picture. Literally, it's like you really see the structure of the language in the diagrams. I mean, these were very simple diagrams I had, but you see that, and I don't think that anybody could do anything like natural language processing on a quantum computer without the help of that structure. Like if you do it brute force, like the big language models do, would be impossible, because it would be impossible to train a quantum computer. But it's actually that structure. It's an expansive structure. It's tensor structure and all that lets us even do it for now. And it also makes it interpretable. So in the current discussion about AI being dangerous, we're in a very good spot. We're in a very good spot. So there's a number of advantages. And so in our experiments which we're doing, so we're hoping to demonstrate this year algorithmic advantage, like not just advantage, actually supremacy. We're hoping to show that. Then you got the interpretability advantage. And then you also got the reduction of resources advantage, because you got an interpretable structure, which means something. You need less data and less variables.
Yes. Yeah. Thank you for a wonderful talk. Thank you. Yeah.
Anyone else? And any question?
I wanted to ask a question regarding your pictorial method. So is it that only processes which has time ordering can be represented through this pictorial order, or like any general process can be represented?
So there are papers already using this sort of language or similar to do like indefinite causal structures.
Yeah.
So Alex Kissinger has a paper, has quite a number of papers, Giulio Chirabella's papers where you use the same formalism to deal with indefinite causal structures. So no, it's the way you have to think about it is like, in that case, you don't stop at process. You also stop at higher order processes which change processes. What people call combs, these combs.
Okay.
This actually is true for language too, by the way. If you got an adverb, let's think of a verb will be a gate. We typically think of a verb as a gate, and an adverb will be something acting on a gate, modifying that gate. That's what an adverb really does. So you need to go to higher order processes to capture all these things, but then there is no problem.
But will it give an advantage in the pictorial method?
I mean, in a lot of the sort of indefinite causal structure stuff, people are just using these graphical language because it's just easier. I mean, superoperators are pretty horrible things in Hilbert space.
Yeah, but what sort of constants will you have here, like the pictorial constants? How will you transform one? Let's say I have the algebraic expression. How can I convert it to a pictorial constraint or something like that?
How can you what?
How can I convert that into pictorial sense? Like let's say I have a constraint, algebraic constraint, and I want to visualize it pictorially. I mean, what kind of how can I transform that language into this pictorial thing?
Okay, so at the moment, what I've been talking about is a context where you, for example, don't have differentiation or integration or exponentiation or Hamiltonians. Now, if you go to some recent papers by us, then you'll see that we have now developed these diagrams also to do like analytical stuff, integration, differentiation. There is a bunch of papers which are about like how to formulate field theory, quantum field theory in this language. So you have to look for papers by Stefano Goggioso, who does this. So this sort of developments to like general physics are still very much in progress.
Mm-hmm.
But we since recently we've got essential ingredients there. So we are now, for example, studying with the chemists in our company to see whether we can get an advantage for quantum chemistry. So they give an Hamiltonian and we start to study Hamiltonian diagrammatically. That's ongoing research.
Okay, thank you.
I'm not really hearing.
Anyone else? Okay, if not, Bob, thank you again for a very wonderful talk. It was nice having you here.
Okay, thank you. Bye. It's lunchtime here.
Yeah. Thank you, Bob.
Bon
Yeah.
appetit.
Bye. Yeah.
Thank you, Tavi. It's very wonderful talk. You know, this guy is so creative, Bob.
Yes,
My
yes.
God.
Thank you.
Wonderful.
Thank you. Cheers. Bye. Cheers.
Bye bye.
Okay then. Bye-bye.
Bye.
So, Swami, we log out for tomorrow?
Yeah. So I think we'll end the session now as we have no more talks. And tomorrow the session starts at 9.
Achha,
9, right.
Yeah.
Okay.
With
Please send a gentle reminder to all. Huh?
yeah.
It
We'll
starts
send
at 9.
we'll send the mail to everyone.
Yeah.
And I think tomorrow the first talk is from Professor Barry Sanders.
Very
Yes.
Yeah.
Okay.
Thank you.
Yeah. Bye.
Okay. Bye.